Modern text-to-image AI can summon a high-resolution world from a handful of words in seconds. The visual fidelity of these models has outpaced our ability to fully understand what they are actually building. Beneath the photorealism, the latent space is constrained by the data that built it. Training datasets scrape billions of images from the web, carrying over deeply embedded societal imbalances, occupational stereotypes, and cultural biases. The me input a neutral prompt, like asking for an image of a doctor performing surgery. The model doesn't generate a purely randomized medical scene. It defaults to a specific, statistically skewed demographic profile of who it calculates a doctor should be. We know these biases exist, but our current methods for auditing them are fragmented. Researchers typically measure a single metric, like gender parity or skin tone in isolation. Measuring generative bias on a single axis can obscure the broader behavior of the model. A system might achieve parity in one category while simultaneously amplifying stereotypes in another. This is the T2I-BiasBench framework. It is the first unified pipeline designed to capture structural flaws in diffusion models. It evaluates 13 specific metrics simultaneously, processing generated images, extracting their semantic attributes, and running tests for statistical fairness, diversity, and contextual alignment. Applying this framework revealed two critical blind spots in how we understand AI generation. First, it proved that models actively amplify bias mathematically beyond the baseline of their training data. Second, it uncovered that visual constraints in an image can artificially mask measurable bias, tricking standard safety checks into reporting of fair outcome. Auditing these systems accurately requires moving past simple demographic parity. Tracking multidimensional variables simultaneously provides a more detailed mapping of model-wide behavior. The experiment starts with input methodology. Researchers fed the models prompts that intentionally lacked specific demographic information, asking for a beautiful person or a doctor. Any resulting demographic skew points directly to the model's internal defaults. To analyze the outputs, the researchers generated over 1,500 images and used ChatGPT-5 to create highly detailed captions for each one. This extracted structured semantic attributes like gender, skin tone, and cultural markers into a measurable dataset. These attributes are fed into the composite bias score, or CBS. This equation aggregates parity difference, Shannon entropy, and contextual association into a single number between 0 and 1. 0 represents perfect fairness, 1 indicates maximum bias. The test evaluated 3 compact open-source diffusion models, Stable Diffusion version 1.5, BK-SDM Base, and Koala Lightning. These were benchmarked against one high-capacity proprietary model. That baseline was Gemini 2.5 Flash, a model heavily aligned using reinforcement learning from human feedback, a standard industry technique designed to maximize safety. By comparing small, open-source models against a large, tightly aligned system, the researchers could test exactly how parameter scale and alignment techniques affect the persistence of bias. The results from the beauty prompt showed an immediate discrepancy. When asked to generate a fashion magazine cover featuring the most beautiful person in the world, the open-source models collapsed into severe demographic homogeneity. This chart displays the ethnic breakdown for that specific prompt. Stable Diffusion 1.5 and BK-SDM output images featuring white subjects over 74% of the time, almost completely ignoring the other 5 ethnic categories. This severe skew triggers a metric called bias amplification. This formula calculates whether a model's output deviates so far from uniform parity that it actually exceeds the historical imbalances present in its original training data. This graph plots bias amplification scores across tests. Look at the beauty column. Stable Diffusion 1.5 and BK-SDM exceeded the critical 1.0 threshold. Compare that to the green bar representing Gemini. The RLHF aligned model maintained near-uniform ethnic coverage, keeping amplification well below the threshold. The open-source systems actively reinforce historical prejudices. Their mathematical generation processes worsen those stereotypes with every image they render. This chart maps gender distribution across the 4 models when asked to generate a doctor, and the variance is extreme. The Koala model produced male subjects 91% of the time, the most severe professional gender stereotype recorded in the entire experiment. On the exact same prompt, Stable Diffusion 1.5 registered a composite bias score of 0.06, the lowest, most mathematically fair score of the study. But that score is an illusion. The researchers identified a mechanism causing this discrepancy, calling it visual attribute occlusion prompting. In over 40% of Stable Diffusion's outputs, the model generated thick surgical masks and caps that physically obscured the subject's faces. Because the attribute extractor could not physically see demographic markers, it couldn't assign a gender, effectively zeroing out the bias penalty. Gemini's response to the same prompt exposes another flaw. Its safety alignment aggressively counter-stereotyped, outputting female subjects exactly 100% of the time. Because standard composite scores only measure deviation from an equal split, Gemini's 100% female output registers mathematically as maximum bias. This is a metric polarity artifact. The equation penalizes extreme overcorrection exactly the same way it penalizes extreme stereotyping. Basic parity metrics can be tricked by a surgical mask or completely skewed by an artificial overcorrection. Relying on them as standalone safety checks is mathematically inadequate. The third test asked the models to generate people celebrating a festival in India. India has hundreds of distinct regional festivals, but the AI outputs showed striking visual homogeneity. The geographic and cultural breadth of the prompt was ignored. To quantify this, the researchers introduced the cultural accuracy ratio, specifically designed to track the diversity of regional markers. The data showed that the models systemically collapsed the vast cultural complexity of India into a narrow, generic representation, overwhelmingly defaulting to visual motifs from just two dominant holidays, Holi and Diwali. Despite easily handling the demographic tests, Gemini failed this cultural evaluation alongside the smaller open-source models, scoring a perfect 1.0 for cultural stereotyping. Modern alignment techniques optimize for surface-level demographic parity. When tested on deep, region-specific knowledge, alignment breaks down, revealing a severe lack of cultural coverage. This graph plots the composite scores across all 5 prompts, providing the complete picture. Notice the culture column on the far right. Every model struggles here. Increasing parameter scale doesn't automatically equate to lower bias. Underlying training data composition still plays the dominant role. The framework does have limitations. As the Gemini artifact demonstrated, its inability to distinguish between a negative stereotype and a progressive counter-stereotype, the directionality ambiguity, is a mathematical constraint that requires human context to interpret. Building a single, perfect fairness metric is a mathematical impossibility, making continuous, multidimensional auditing a permanent necessity. Checking an AI system for gender parity or skin tone distribution in isolation is no longer a sufficient safety standard. We must track semantic fidelity, hallucination rates, bias amplification, and cultural accuracy simultaneously. The 13-metric approach provided by T2I-BiasBench sets a new baseline for what a thorough evaluation actually looks like. The open-source AI community must integrate these standardized semantic auditing tools directly into their base development pipelines, catching these structural flaws before deployment. Standardized auditing provides the granularity needed to identify where models succeed and where their representations collapse.